Good afternoon. This is Andy Schweitzer, and this is a video on covalent bonding. And for this video, we are going to highlight essentially the Lewis structure, or you might even say the development of the molecule. How do you create a model that's going to somehow show us how this molecule works? So a couple things I just want to make sure everyone is aware of is that when I want to create a Lewis structure, I'm referring to something that is covalent. So for example, we have water, H2O. I can draw a little molecule of this thing. Again, the outside line is just to show you the edges of the molecule. I could do something like carbon dioxide. All right, like this, or a nitrogen gas molecule like this. And I'm going to include the rest of my electrons on these guys. All right, so these are all examples of Lewis structures. They have to be covalent. So these dashes stand for shared electrons. Each dash stands for 2 electrons. This stands for 4 electrons. This stands for 6 electrons that are being shared. I cannot do a Lewis structure for an ionic compound. They don't share electrons. NaCl. Can you draw a Lewis structure for NaCl? No, you cannot. It is not sharing electrons. NaCl does not form molecules. It forms a bulk crystal, not a molecule. So, Lewis structures are just for molecules. A few things that I will note about this that you'll want to have some general understanding of, and about the sharing of electrons. Okay, just some piece of information. We have a single, we have a double, we have a triple bond. So single bond, we have a double, and we have a triple. We have bond length. You should be aware that it gets longer and shorter. Bond energy, often referred to as bond dissociation. Energy. This is the amount of energy to break and or form a bond. And you should note that it increases as we go down. This is not really indicating anything involving stability. Instability, okay, nitrogen molecules, 80% of our atmosphere is nitrogen gas, quite stable. Nitrogen triiodide, extremely unstable. This will break down almost immediately on contact to form nitrogen gas and iodine particles, and molecules. So it's involving the amount of energy that you have, not necessarily stability. Okay, we have bond order. Okay, bond order is a number that is indicating sort of your type of bond. You could have, let's say, a single bond would be a 1, a double bond would be 2, a triple bond would be 3. Okay, what you do for a molecule is essentially you take your number of shared electrons and you divide by the number of bonds, and you say, okay, well, if carbon dioxide has 4 total pairs of electrons, and divided by 2 equals a double bond, which is 2. So a shared will have 2 pairs of electrons being shared, or a bond order of 2. it's possible for a molecule to share a double bond across many locations. And we'll see that a little more later on in this video, where this would be 1, 2, 3, 4 bonds, and then it's in 3 locations. So that means each of these guys is 1.3 bond energy, bond order. Okay. Either way, these are things you're going to want to sort of tucked away in the back of your mind as far as bonds are concerned. Now, when creating a Lewis structure, okay, we're looking to create a model of our molecule. You'll want to be very good at this and be able to go very quickly with this. But start out with something simple, let's say like water, H2O. Step 1 is electron inventory. This is only for valence electrons. All right, so hydrogen has 1 valence electron, and there's times 2 for 2 electrons from that guy. The oxygen has, well, there's 6 valence electrons, times 1 equals 6, and 6 plus 2 is 8 valence electrons. So that's done. All right, build a skeleton structure. Now, generally, the first item listed goes in the center, unless, of course, that is hydrogen, because hydrogen can only bond 1 time. Okay, it can only bond 1 time. Therefore, it cannot be in the center of anything. It's always around the outside edges. So I'm going to put oxygen in the center and so hook it with single bonds all the way around. So the skeleton structure simply uses single bonds. Okay. Now again, each dash stands for electrons. So I've used 4 electrons of my 8 original to just set up my skeleton. Okay. Now, add electrons to fill octet rule. So in this case, and I have duet rules, means that okay, the hydrogen follows the duet rule. So hydrogen, when it bonds, it only gets 2 electrons. So therefore, when it bonds, it's done. It cannot do anything more, cannot have any extra electrons around it. This would be a violation. You cannot have this. They cannot have any extra electrons around them. So the way I do this is simply start adding electrons to give an atom 8 electrons, and then I move on to the next one. So 2, 4, 6, add in pairs, 8. When an atom gets 8, I stop and move to the next atom. And I'll stop when I reach my max electrons of 8. Of course, I'm adding 4 more, but I add those 4, 2, 4, and then I continue adding, counting from there. 2, 4, 6, 8, I'm done. Okay. Does step 3. Add electrons to fulfill octet rule. That's what I just did. Share to fulfill octet rule. If we're after adding, you still don't have everyone having the octet rule satisfied, which you should know if an atom has the octet rule satisfied, because you're giving them those electrons along the way, then you would want to share to complete the deal, to get them fully to 8. All right, so let's try another example. Okay. Again, these will, as the example I grab, we'll go through various types of examples that will show little wrinkles. Okay, so now let's do nitrate. Okay. Now nitrate is going to be something along the lines of, okay, Lewis inventory. This is going to give me 5 electrons. This is going to give me 3 times 6 is 18. And then grand total 23 electrons. Okay, add that up. We have 23 electrons. This number almost indefinitely has to be even. If it's not even, then we have a lone electron, which would be called a radical. And very unstable, does exist, but unstable. So really 99.99% of our examples, our N count will be even. So why is this not even? Well, we gained an electron here. Okay. So I need to add 1 more electron to form 24 electrons. It's a common mistake for someone to subtract an electron off, but that's not what we did. We have a negative charge, means we gain an electron. Okay. Next step, draw out Lewis structure, skeleton structure. Top, bottom, does not matter. This is a two-dimensional picture of a three-dimensional object, so we're not showing all of our angles here necessarily. I mean, I'm not showing that this is a 90-degree angle. It simply is flat, a three-dimensional drawing on a flat piece of paper. So it's not 100% correct. So I use up 2, 4, 6. Now, electrons, just to get to my skeleton structure. So what I do is I start counting from 6. 2, 4, 6, and I add electrons. I usually do the center one first, because then I can share in any direction I want. And then move to the next atom, just giving 8. 2, 4, 6, 8, 10, 12, 14. Again, this guy, the dash counts for both guys 8. Nitrogen has 2, 4, 6, 8. And the oxygen now has 2, 4, 6, 8. So I've added electrons to give each item 8 and move to the next atom. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and I am done. I cannot add 2 more electrons here, even though I would like to. The deal here is it's short 2 pairs, even though I've added all my electrons. So the last step, share with a neighbor. Take these 2 off of here and add between. This is now a double bond. If I'm short 2 pairs, I would use a triple bond. We have single bond, double bond. It is a charge of -1, so we just draw a bracket on this thing, and we indicate that charge in the upper right-hand corner, like so. Now, there is been experimentation on the molecules like the nitrate ion, and they found that it is not a single, and a double. It is a something between a single and a double for everyone. So it turns out that this double bond is smeared across all 3. So like I said, it's a 1 and a third bond as opposed to a single, and a double. Bond order 1.3, 1.3, 1.3, not 1, 1, 3, 2. All right, so we call this smearing a resonance structure. Okay. The way we show it, whether students like it or not, is to show each option. That the nitrogen is now on the bottom, the oxygen is double bond at the bottom. Now the actual atoms are not moving, which sometimes kids like to mistake that. The atoms are solid, and they cannot move. But the electrons are more fluid, which means they have the ability to jump around a little more. This is going to have 3 resonance structures. Okay. Other than that, that's pretty much it. If you don't have a charge, you don't need brackets. Okay. Simple Lewis structures. Now, this is what we would have covered in the general honors chemistry. As you build your Lewis structures and as you draw your double bonds, it tells you the type of bond, type. And it shows you what I call connectivity, which who's connected to who. That's pretty much about it. There are other ways to potentially arrange things, okay, and that is where we'll get more into something we don't generally cover in general chemistry or honors chemistry, which would be a formal charge, okay. The last thing I want to talk to you about here in a moment would be the octet rule exception. So the octet rule exception means, okay, is it possible for an atom to hold more than 8 electrons? Okay, and what do you do if an atom does contain more electrons? And that would be in a situation where if we have, let's say, like sulfur hexafluoride. This is going to look like this, sulfur. The molecules we'll be using for Lewis structures are relatively symmetrical, and everything comes off the center for the most part. Okay. In this case, we have 2, 4, 6, 8, 10, 12. The sulfur has extra electrons, and it's violating the octet rule. So how do you know if it can violate the octet rule? Well, we're looking at the periodic table, and any central atom that is in the third row or lower, meaning that it is going to have d orbitals. Okay, d orbitals can hold more electrons, and therefore, technically, the octet rule works really good for the second row, but the third row is bigger, so theoretically, it can hold more than 8 electrons, sharing 4 times. So at this point, 6, let's say prongs coming off the outside edge is the most that I currently have seen. So 6 connections. So SF6 is pretty much maxed out. That's 6 bonds total, not 5 singles and a double, 6 bonds total. Sometimes we'll go through a molecule and we'll hook up all of its substances around the outside, just a generic molecule, and we'll have extra electrons left over. We put them on the center atom, like so. All right. So any excess electrons go on the central atom, and the central atom can do this, exceeding 8 electrons, if it's in the third row or lower. Thank you very much.